for tangent to have an inverse, we again restrict the tangent function on a subinterval. For example, just the interval, not on all the intervals where tangent function is defined. So we only consider this restricted domain where the tangent function is increasing. So from this, it is a one-to-one, then we can find its inverse. So that is, we look at a branch. So this tangent function over this interval, right, with positive half of pi as a vertical asymptote and negative half of pi as a vertical asymptote. Although we know this is a periodic function, there are other branches, and then we just do not consider. We just only look at this branch, the graph in blue, that is the tangent function on this interval from negative half of pi to positive half of pi. Then it is one-to-one. It will pass a horizontal line test, and it is one-to-one. And then if we look at the domain of this function, you see y equals tangent x. The domain is from negative half of pi to positive half of pi. And the range is all possible real numbers. So that is from negative infinity to positive infinity. And if we consider the inverse function, the y tangent inverse, or we can also say arctangent x. Yeah, for the inverse function, domain will be any real number. Yeah, from negative infinity to positive infinity. The range will be negative half of pi to positive half of pi. So keep in mind, so as long as we know domain and range of the original function, and then its inverse will be, yeah, we can also know domain and range of the inverse. So let's again try to do a sketch of the tangent. We already used this technique for sine, cosine inverse, and now we want to do a sketch of tangent inverse using some sample points. So first, consider the tangent function from negative, but not including negative half of pi, to positive half of pi. Recall that this at negative or positive half of pi tangent is undefined, right? We saw vertical asymptotes. So therefore, we pick the points that with x coordinates bigger than negative half of pi, smaller than positive half of pi. So we just pick these x values. At each one of these x, we can find corresponding tangent x. So for example, negative pi over 4, the tangent value is -1. So we know this special special angles, right? At each that tangent will be special value. We know its exact value. So tangent at negative pi over 6 is negative square root 3 over 3. And tangent 0 is 0. And tangent at pi over 6 is square root 3 over 3. At pi over 4, tangent pi over 4 is 1. So after we have this, then we know we can reverse. For each time we have a value AB, we know that BA is on its inverse. So let's create a table immediately for the inverse tangent. So if you just do a quick comparison, this table is simply based on the above table. So you see this, and if your input is -1 for the inverse, the value will return the negative pi over 4 inverse function. So, and if you provide 1, the inverse function will give you pi over 4. That's why we have 1 pi over 4 in the table for the inverse function. So inverse tangent, we have 5 points. And then we can show them. So you see the black curve is the tangent x. The purple curve passing through the right dots, right? Those are the dots on the inverse. So we can see the inverse. Its domain is on all real numbers for any real number. Yeah, I should use open parentheses. And the range should be, that is the range for the tangent inverse, should be from negative, okay, should from negative half of pi to positive half of pi. Yeah, this is to see for the tangent, because the tangent, recall this tangent is a function you are very familiar with, right? We only looked at the tangent function, which is the blue curve, from negative half of pi to positive half of pi, because only for this tangent function, and we did our inverse. So that's the domain for tangent. Of course, open parentheses. So we have domain, and the range for the tangent will be all real numbers. So the inverse tangent function, which is the purple curve, yeah, has the domain, which is real numbers. And the range of the function will be, for all possible y values, will be this interval. So here you get a good look. And certainly these two curves are symmetric about y equals x, right? If you draw the curve, you can see the symmetric property. And the tangent original curve is increasing, this inverse is also increasing. See in the, so we can now, after we see the inverse tangent curve and its domain and range, then let's do a number of evaluations. just to make sense with this function. So we want to evaluate tangent inverse at square root of 3. So this is the value you're trying to determine, the y value, when this function has the input square root of 3. What is the specific y value? And this y must be such a y whose tangent is square root of 3. And realize this y, which must be in the range of tangent inverse, that means y must be in that interval. Or you can look at this part, this tangent y, right? This only for which tangent? Only when this domain of the tangent is that interval, right? That's also the range of the inverse tangent. Okay, so that is the meaning. So can we figure out this y whose tangent is square root of 3? So if you recall this, in this interval, there is a y so pi over 3, pi over 3 is such an angle. Pi over 3, this at this, whose tangent value will be square root of 3. Okay, now, yeah, there's a unique y, you see, because inverse is a function. There's only one unique y that is corresponding to this x, which is a square root of 3. So you found it. Now, do another problem, arctangent -1. So it's a very similar analysis. We just try to get used to these names. Arctangent at -1. So when this is an inverse, right? We know it's well defined for -1. Because your input can be any real numbers for this inverse tangent. So if it's -1, what are we looking for? We're still looking for a particular y value, which is the inverse function value at -1. And this y has to be what? In what interval? In that interval, such that tangent y is -1. So we know this y is a negative pi over 4. So that's the answer for the second problem.